Hello everyone, welcome back to ML with Philip. In this video entitled RNNs Tutorial Generating Names in Different Languages, I want to walk through with you step by step how we can build a recurrent neural network that's going to be able to generate new names in a specified language. This is part 2 of my series on natural language processing entitled RNNs from Scratch. In this video, we continue where we left off in part 1, where we built a recurrent neural network in order to classify the language of origin of a data set of surnames. What we are going to do is we're going to take the code and the recurrent neural network that we built in part 1, and we're just going to modify it in order to change it so that instead of predicting the language that a name belongs to, it's now going to try and predict the next character in the name. So if you haven't seen part 1, then I encourage you to pause this video and go back and watch the first video so that you can understand where we're starting from. I'm going to provide a link for that video here, so please go to that video and watch it if you haven't already. I also want to give credit to where this tutorial originally came from. All of the code from this tutorial and this tutorial as well has been inspired by a tutorial from PyTorch's website, which you can find and I will link in the description. And it is called NLP from Scratch, Generating Names with a Character Level RNN. So I encourage you to take a look at that tutorial on PyTorch's website as well. With that said, let's get started. All right, so before we get into coding up the RNN to generate names, I want to draw some diagrams and explain the structure of the RNN a little bit so that we're clear on what changes need to be made and what exactly is going on. Okay, so let's redraw the RNN cell that we're used to seeing. So it takes in an input at the previous time step. And this is time step t. This is time step t equals 1. And it takes a hidden state at the previous time step. And it makes a prediction for the current time step. And it outputs a new hidden state for the current time step. Okay, in our case, we have a surname and we are trying to train the RNN to predict the next character in the name. Let's say that our surname was Smith. Okay, what happens is we're going to have time steps. T equals, we're going to start at t equals 0. So we're always going to be given the first letter. And then we're going to go to t equals 1, 2, 3, 4. And then we're going to have a special character called an end of sentence token that indicates that we have reached the end of the word. In addition to the name, we also are given a language. So we know that the language is equal to English. So we're also going to have to take in the language as an input as well. We're going to take in, so this is for time step t equals 1. We're going to take in the hidden state at t equals 0, which is just going to be a 0 vector. We're also going to take the input at t equals 0, which is the letter S. Now, in addition to this input, we're also going to take in another input, which is going to be the language. So we're also going to take in an additional input, which is the language, which is equal to English. These are all of the things that are going to be inputted into the RNN. That's all of the information that it's going to get, and it's going to produce an output, y1. The target that we're trying to predict is the next character m, so we hopefully will predict that the next character is the letter m. However, we might make a wrong prediction and predict that the next character is the letter D, for example. Okay, and then we have the hidden state, the new hidden state, H1, that gets outputted. Okay, and we predict the character D, but we want to check if that's equal to the character at x1, which is m. We make a prediction for a character, and we want to check it against the input at the next time step to see if we made the correct prediction. And then we go on. So now our next time step, this is t equals 2. We're again going to take in English, as the language. We're going to take in x1 is equal to m. We're going to take in the hidden state, h1. And we're going to produce a prediction for the next time step, t equals 2. So we're going to try and predict the character I. And so we'll make another prediction. Let's say this time it's the letter F. And again, we want to evaluate if that is equal to x2, which is I. And then we produce a new hidden state. And we continue this all the way to we reach the final, all the way until we reach the final character, which is the end of sentence token. So we continue all the way until we reach the last time step. So t equals 5. And in that case, we have x4 is equal to h. We are always inputting the same language, and we are taking in h4, and we're producing a prediction, and let's say it's the character G, and we're hoping that this prediction is actually the special character which indicates the end of the sentence. So we're hoping that this would be equal to x5. Okay, and we produce a final hidden state at the end. So that is the structure of our RNN. We can see how it iterates through every character in the sequence and how it makes a prediction for the next character, and then that prediction gets evaluated and it passes along information through the hidden state along each time step. Okay, so one more thing I would like to look at is how does the actual structure of our RNN architecture change from the RNN architecture that we had before? And truthfully, it doesn't really change much. So let me draw out the architecture that we had before. Okay, so we would take in a hidden state, ht, which is just a vector. And we would take in an input, ht minus 1, xt minus 1, which is also just a vector. And we would combine them. So we would concatenate h at t minus 1 and x at t minus 1 to create a new vector which just stacked both of these together, ht and xt. Okay, now we just have an additional input which is called the language. So I'm just going to call that L, and this vector doesn't change. It's always going to be the same from each time step because the language is always English. So I'm just going to call this the language vector, L, and the L vector gets passed in here as well. And so now we have we concat h, x, and L together. And now we have this new vector which just contains all three of these inputs concatenated together. And sorry, this is t minus 1. Okay, from there we just go through a linear layer. We go through a linear layer. And this linear layer is going to produce a new hidden state h of t. Hidden state, and we're again going to pass it through another linear layer. Pass it through another linear layer. It's going to produce an output, and that output is going to then get passed through a softmax. And then it's going to become the output. And then our next hidden state h of t just gets passed along. If you actually look at the architecture, nothing has really changed. The only additional thing that we did is we just included this language in with our input, and they all just get combined together into a single vector. And then we still pass it through a linear layer to get the hidden state. We pass the hidden state through a linear layer and then through a softmax to get the output. And we pass along the hidden state as an output. Now we're ready to start coding up our RNN. So we're going to start with the code that we had from the last video, where we learned how to classify the language that names belong to. What's going to change in this tutorial and in this RNN is that instead of trying to predict the language that a name belongs to, we're actually going to take the language as an input, and we're just going to try to predict the next character in the name. We have all of the same code as before. So let's rename this Okay, now let's run the code from before. So we have all of our data, same as before. We have a dictionary with each language and a list of names. We've also encoded all of the letters in our vocabulary. One thing that we actually want to do is we want to add one more character, and this character is going to be the end of sentence token. So instead of taking all of the letters, we're actually going to take all of the letters and we're going to add one more special token called the end of sentence token, because we want to predict when a name is finished. So this is going to be our new set of characters. So let's do that. And let's make sure that works. Okay, great. Okay, and now our vocab length is one more than what we had before. The name to tensor function is still going to do the same thing that it did as before. So if we have a name such as Smith, it's going to encode the name as we expect. Now, since we're also going to be taking the language as an input, we will want to encode the languages as well. So we're going to want to encode all of the languages in a similar fashion, assign all of them an index, and then one hot encode them. So all of the languages are these are our set of languages. Okay, so now we want to just enumerate them. Okay, perfect. And then we just invert that to get the language back to the index. Okay. So that looks good as well. Now the only thing that we need to do is to just one hot encode these languages. So what we're going to do here is we're going to get the number of languages, which is the length of langs, and we're going to create a vector of zeros with the length of the languages. And then we are going to do, let's see, the tensor is equal to this. And then let's say our language is English. Then we will also need to find the index associated with that language. So lang2 index of the language is 9. And then we're going to want to take the tensor at that index and set it to 1. So our new function, lang2 tensor, is just going to look like this. Okay, great. So we have that. Okay, the next thing that we want to do as well is we didn't have a specific function before to encode the target because our target was super simple. But now we have a more complicated target. So we want to create a function to represent our target as well. When we used our NLL loss, all we had was we had the index of the correct language that we were trying to predict. So now all we need to do is for each character, we need to get the index of that character. So we have this name. Let's say our name is Smith. So all we need to do is we just need to take the index of each character in the name. And that will look like this. We want to predict the next character. When we're at the index of 0, we would take S in as an input and we would be trying to predict M. So our target would actually have to be at the next index. So we would have to shift everything over. And in addition, we also want to predict one extra character, which is going to be the end of sentence token. So what we're going to do is we're going to take our name, convert it to a list, and we're going to add the end of sentence token. So we'll do that. And now our name looks like this. Now when we get all of the indices, we actually have one extra. So because, as I mentioned, we're predicting the next character, we're actually going to want to remove the first index. So we're actually going to do this. And this is what our tensor looks like. So at index 0, we want to try and predict the letter M, which is the 12th index. At index 1, we want to predict the letter I, which is index 8, and so on and so forth. So this is the function that we're going to create in order to convert our name to the target. And we also want to make sure that this is a torch tensor. Let's just wrap all of that in our function. All right. So I think we're good now. Let's just test everything here. So we have a name, and it is Smith. We have a name tensor from our name. That looks like this. Great. We have a language, which is English. We have a language tensor, which is okay, and we have a target. Okay, perfect. Everything seems like it's working as we expect it to. Now, let's take a look at our neural network. As we saw in the diagram, we actually don't have to change very much. The only thing we have to do is we just have to add the language as an input. Let's leave our neural network as it is and just make sure that we can pass a single example through the neural network. Okay, so we haven't changed our neural network. Now let's pass an example through our neural network. So let's kind of copy this code that we had above. This is a little trick to move things down. So, okay, we know that all of this works as it should. We need to take the name tensor at the first time step. We also need to initialize our hidden state. Okay, and now let's go output, comma, hidden is equal to RNN of hidden name tensor at 0, hid and the hidden. And let's define our criterion as well. Okay, and now we got an output, we got a hidden, everything looks good. Let's evaluate our loss at the target at 0 and our name tensor, our output that we got. Criterion. And we got an error. Okay, so we just mixed up the order, but now it seems like it's working. Okay, and so it seems like our neural network is working. And now if we were to go to the next time step, we would then go output hidden is equal to RNN of name underscore tensor at 1. And our output would be this. Our target would now be that. And we would calculate the loss of the next character predicted. Everything's working with our neural network, but we want to make that change where we add to the input, we add the language to the input as well. What we need to do is we need to take the input and the hidden, and now we want to add the language there as well. And we're going to just concatenate the language, and we're going to have to make the dimensions work. So now this is going to be the input size plus the hidden size plus the number of languages. Okay, so we do all of this and we add in the language tensor. And we do this again, just to make sure. And everything seems to be working. Great. So now let's try and train this neural network and see what we get. Okay, so in here we have to make the same adjustments. We have the language and the name. The target now is going to be name to target of the name. The language underscore tensor is going to be lang to tensor of the language. And we are going to add that in as the input. We're actually going to be calculating the loss at every single one of these time steps. So we're going to initialize the loss at 0. And then we're going to calculate the loss here. We want to calculate, yeah, now we have a new target for every single time step instead of just having a single target. We want to set this to a tensor, and we want to do loss is L is equal to this, and then we just do loss plus equals to L. You notice how we accumulate the loss through every character. We also want to normalize that by the length of the name. So we don't have to do that in the backward step, but we are going to do that here for when we calculate the average loss. So we're going to just divide this way. And now let's take a look at what we get. So we're getting an error here which says that target 57 is out of bounds, and that's because we didn't adjust our output dimension to match the number of characters. We were still using the same output dimension from before, which was the number of languages. So we need to make that change as well. So in defining our neural network, the output size is no longer the number of languages, it is the number of the vocab. And let's give that a try. Okay, great. Looks like our loss is steadily decreasing. So let's give it a few minutes to finish running, and then we'll check back in and see how we did. All right, so we have finished training. Let's take a look at our loss. All right, so wow, it learned very fast, and then it quickly started to plateau. Interesting. So let's see what, let's take some predictions and see what our results look like. This was our old predict function, but our new predict function is going to look totally different because we're predicting an entire sequence now. So let's start working on it here. So of course we're going to need we're going to copy some of the code that we used up here. So in this case, we are actually going to be given a language and a name. So language is equal to English. Name is Smith. Okay, so we've trained our neural network and the training looks good. Now let's actually generate some predictions and see how our neural network performs and what kind of names it's going to come up with. Our prediction is going to be completely different than the prediction that we had for classifying names, because now we need to generate an entire sequence. We can take some of the code that we used for training the neural network and start with that. Now, instead of being given a name, we're going to be given a prompt or some starting letters. So let's say we're given the starting letters SM. Okay. We also need to be given a language. So let's say that it's English. And our input is now going to be, well, our initial input is going to be the first starting letter. Okay, and then we also need to index into the first dimension our language tensor, and we don't need a target any longer. So we have our hidden, our input, and our language tensor. Okay. And then we calculate an output and a new hidden state. All right, so let's try that. So this is our input. That's the encoding of the first starting letter. What we need to do is we first need to iterate through our entire starting sequence. We have to iterate through S and M and let the RNN pass the information along. And then we only start actually generating letters once we've iterated through all of those through all of the starting letters. We would actually take our input now at the next time step, and we would now again calculate a new output and a new hidden. We started by inputting the letter S into the RNN, and it generated an output. However, we didn't use this output because we already have the next letter, which is M. But we did pass along that hidden state so that it could use that information. Then we inputted the letter M, and now we actually get an output we're going to add on to our word. So the thing is, we need to determine which letter we actually outputted. So what we do is we can use this top K function. Let's see, val index. We predicted the character with index 8. So that would be the character index 2 character. And okay, so we predicted the letter I as our next letter. Okay, so our next letter is I. So we want to start building out our predicted name. So it starts off with the starting letters that we already have. And then we add on the next letter. So this is our predicted name so far, SMI. Okay, and then the next letter is going to become our new input. So now we don't have any more inputted letters, so we actually are going to take the next predicted letter. So we're going to do name to tensor of the next letter as 0 is our new input. We're going to calculate the output. And then we're going to take the just gonna put these together. Gonna do that. And we're gonna then add on the next prediction. So the next prediction is SMIT. So it looks like it's actually predicting the last name Smith, which is pretty cool. Now here's the thing. We want to put this into a single for loop. Now, firstly, we want to iterate through all of the starting letters. Okay, so for I in range of length of the starting letters, we initialize the hidden state. We take in the input to be the starting letter at I. The language tensor also gets initialized. Then we calculate the output, hidden. Okay, this also gets initialized here. Okay, and let's just make sure we're iterating through every starting letter. Okay, great. So that's what we need to do to iterate through all the starting letters. We don't actually have to add on any of our predicted characters here. Now, once we've exhausted the starting letters, this is where we start adding on additional letters. Let's say the max length is 20. which means that we don't want to keep generating characters forever. We only want to generate characters until we either reach an end of sentence token or we want to choose some cutoff point. So let's do this. And since we've already gone through 2 iterations, let's do, so that way. Well, now we no longer take the input from the starting letters. The input is going to be our previous output. So what we'll do is we'll just calculate the next output, and we'll calculate the next predicted character. And we're going to take the next predicted character to be our next input. So notice how here we calculate the input first, and then we generate the output. Here, our input comes from the output, so it actually comes afterwards. Sorry, we actually have to calculate the input from the previous output first. So input is equal to, we have to do this on the last prediction. So we have to do this on the last prediction to get our input before we can use the input. Otherwise, we would have been using the input as M instead of whatever the prediction was. So let's fix that little piece. And let's try again from the beginning. Okay, so it didn't actually predict Smith. It ended up predicting Smite and Smiter. Interesting last name, but pretty cool to see what our RNN actually comes up with. All right, so now it's getting an error. So the error is we are actually predicting an end of sentence token here. And what it does is it tries to treat this end of sentence token as a name when we do name to tensor. So what we actually want is, if we get an end of sentence token, we want to break. So if our next letter is the end of sentence token, we're done. Otherwise, we'll continue generating until we've either reached the max length or our RNN has predicted the end of the name. Sorry. We have to start it from the beginning. Okay, great. So we can see what's happening here. It predicts the end of sentence token at the end, and then we stop. Awesome. Let's wrap this into a function, and we'll call this and now let us do cool. So we were able to generate a completely new name with our model. Let's do this with some other examples. Let's use the starting letters SM, and we'll do we'll make a prediction in every single one of the languages. Okay, so with the prompt SM, we were able to generate the name. I'm just going to put some spaces here to make it more readable. Smarak, Smerer, Smara, Smiomi, Sma, Smi, Smingovaki, Smaran, Smangala, Smara, Smios, Smingo, Smara, Smits, Smersen, Smo, Smanak. Pretty cool. Let's do some random letters. For letter in random dot sample of A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, W, X, Y, Z. Just sample 5 random letters. And let's generate some predictions in all of the languages. Okay, so for the letter F, we got Franto, Freter, Farsui, Farinov. Interesting. Some pretty interesting results and pretty impressive. These actually sound like last names. You know, V is definitely a Vietnamese last name. Vin seems like it could be a true Chinese last name. Lawaki seems almost like a Polish last name. So those are the results of our model. It's pretty impressive. It's able to generate some names that really do sound like last names from different languages. So it's very interesting to see how we were able to build this model together. And the structure of the model is very basic. And I'm actually going to just fix one little bug that I just noticed. And that is if our next predicted letter here is the end of sentence, then we don't actually want to continue. So if the next letter is the end of sentence, then let's just return the predicted name, which will immediately return the result and take us out of this function and not continue with anything else. All right, so at this point, we have been able to train an RNN to learn how to generate names in different languages. And we were able to use it to make some predictions and to generate some names. Now, what I want to do next is I want to make some changes to the architecture. We used the RNN architecture that we had from the previous video where we were solving the classification problem. But now I want to slightly improve the architecture to better handle the problem that we're solving now, which is generating names. So I want to start with drawing a diagram of the current architecture that we have, and then I'm going to draw a diagram of the new architecture that we want to implement. This is what we have in our current architecture. We have an input, and we have a hidden, and we have the language. We take all 3 of these, and we input it into our RNN, and we concatenate. We concatenate them together to create a combined input. The next thing that we do is we pass the combined input into our linear layer, which we have called input to hidden. And input to hidden will produce a hidden state. this hidden state is going to pass through another linear layer called hidden to output. And hidden to output is going to produce an output. And the output is going to go through a softmax. And then the softmax is going to give us our final output probability predictions. And then that output is going to get passed back in as the next input. And the hidden state is going to get passed back in as the next hidden state in the next time step. So this is our current architecture. And this is going to be our improved. In our improved architecture, we're still going to take in the language. We're still going to take in the input. And we're still going to take in the hidden. We're going to combine all of them in the same way. Now we're going to have two linear layers. One is going to be called input to output, and the other one is going to be called input to hidden. And the first linear layer is going to produce the output. And the second linear layer is going to produce the hidden. Then we're going to combine the output and the hidden together. And we're going to have one more linear layer, which is called output to output. And this will produce our final output, which gets passed through a softmax. And it produces the output with all of the predicted probabilities. And similarly, the hidden state is going to be passed back in, and the output is going to become the input at the next time step. So this is our new architecture. This architecture has some more computational power, and it should be able to give us some improved predictions and a more robust model than our current architecture. So let's go ahead and implement this now in code. Now that we know what the architecture looks like, we can go ahead and start changing the code and implementing this new architecture. Let's go back into our RNN class that we defined here, and let's start implementing the new architecture that we had. We are still going to be taking the inputs, input, hidden, and language, and we're still going to be concatenating them into a combined vector. What changes is we're actually going to have a new layer here called input to output, which is also a linear layer. And we're no longer going to use this hidden to output layer. Instead, we're going to have another output to output linear layer. So we're going to take the output from this layer and the output from this layer, and we're going to concatenate them together. So this is going to have the dimension output size plus hidden size, and it's going to produce an output with output size. So here we combine the input and the hidden and the language. We get a hidden state from I to H, and we also get an output state from I to O. From here, we're going to combine the hidden state, and we're going to combine that with the output, and then we're going to pass that through our last linear layer, which is and this is going to be our new RNN. So let's try that and see if everything works. Okay, we have an error somewhere. So let's see what's going on. Okay, we should be taking in the combined input as the input to output layer. Now everything looks good. Let's try that again. Okay. Seems like everything is working. Let's now train our neural network and see if we get any improved performance from what we had before. So we're going to let that train, and I'll check back in with you soon when it's finished. Okay, so our new neural network has now finished training. So now I just want to recap everything that we've done in this video. We started with the same code that we had from the video in part 1, where we trained a neural network to learn how to classify the language that a name belongs in. In order to solve this problem, which was trying to generate new names by learning to predict the next character in the name, we had to add some new functions and encode things in a different way. So what we needed to do is we needed to add an end of sentence token so that we are able to predict when a surname ends. And we also had to add a encoding for the language in a similar fashion to what we have for the characters. Additionally, we had to create a function to encode our target, because now we have multiple targets for every single time step. And we also had to add an end of sentence token to the target as well. After we were able to make those adjustments so that we can encode all of our data properly, we now define the new neural network. So this neural network, instead of just taking the input and the hidden state, it also takes in the language and combines all of them together to form the input, which is composed of all of our data. And then we made some changes to the architecture as well, introduced several hidden layers, and we were able to improve on the architecture that we had. And we still output a hidden state and an output. This time our output is now the next character in the name. And we were able to validate that everything works by testing it with an example. Then we trained our neural network almost the same way as we did before, except instead of just making one prediction, we have multiple predictions for every single time step and every single character that we're trying to predict. And we just add up the loss from all of those predictions. Then we took a look at the learning curve. And finally, we created a new predict function, which is able to make predictions for the next character. And we keep on generating the next character until we have predicted an end of sentence token, at which point we stop. We combine all of those predicted characters together to get our final name. And then we used our neural network to start generating some completely new surnames that it came up with on its own. And we saw how the surnames actually resemble the surnames from different languages. So that's everything that I wanted to cover in this video. I'm going to create a part 2, an extra video, where we look at some extra things that are interesting to know, but not essential. So in that video, I'm going to cover how we can add a start of sentence token in order for it to generate a new name without any prompt at all, and how to use the built-in RNN and LSTM classes from PyTorch, as well as how to process the entire sequence at once instead of iterating through all of the time steps. If you're interested, that video will be linked at the end and you can take a look at that. That's the end of the video. Thank you so much for sticking with me and watching, and I hope that was useful to you. I'm going to be making a part 2, which is going to cover some additional concepts and capability. So take a look at that if you're interested. If you reach the end of the video, put a comment letting me know that you made it all the way to the end. I know that these are quite long. Check out my channel for more machine learning videos. Like the video if you found this useful. Subscribe to my channel if you want to see more videos like this. And thank you so much for watching. I'll see you in the next video.